Good afternoon, and I will talk about the interconnect we are developing at Mellanox, a little bit about what we have, a little bit about what we are heading to, and then we'll take questions. So the thing starts today. We are in the data explosion phase, where data grows exponentially, and the need for processing the data and looking for what you really need. First of all, there is a big opportunity here, and the second one, there is a big challenge here. Because processing data that is collected today, not only the amount of data, but the way it's actually managed and stored, it's what's called unstructured data. It is a lot of data comes from cell phones and photos and stuff that people keep on the web. And there is a great opportunity to use this data for business and research purposes. Okay, you can have people talk about Internet of Things. So there is going to be, even today there are, and there is a number of sensors, and the number of data sources is growing. And once you have this data available and you can process this data and convert it into information, then there is an opportunity to have a different way, to enable different way of living. Okay, you can prevent traffic instead of avoiding traffic. You can have real-time alerts for the health issues, and you can. And of course, there's a significant amount of business intelligence that can be done. One of our guys in Mellanox was looking for some fishing equipment on the web. And a few days later, he was walking near Santa Row, and he got a message on his cell phone that the stuff he was looking for on the web a few days ago is actually available on the store today. So this is the example how we can use the data and associate the data with growing your business. So ability to access the data at real time requires processing, different processing capabilities. It requires a new architecture of the storage. There is now there is a additional storage tier, which is the flash-based storage servers that have not only significantly higher bandwidth but also much lower latency. And connecting these tiers and connecting to the computing and managing it and running it in a way that it is always available and always up, it presents new challenges on the networking or the media that connects this. And actually, not only bandwidth and the latency, which are sort of the nuts and bolts of network performance, but also the way the network interfaces are exposed to the application becomes critical. So being able to access the data on across the network at lower cost in terms of the target of the data is RDMA, and it significantly improves the performance of applications in general and storage in particular. Basically handling all the networking stack in the NIC rather than the CPU obviously enables to use the CPU for the application. And another trend that we are having now is with this cloud and Web 2.0, people are actually using overlay networks, so basically segregating the physical and logical network infrastructure. So you can have a data center as a service, which is basically public cloud is about. So going to the technology, when you have a big challenge, there is always high-end technologies that waterfalls down. And we talked about the network efficiency, and this is a chart taken from the top 500 analysis, showing basically the CPU utilization or efficiency of the different interconnects. And what you see here is that the blue dots, which is InfiniBand interconnect that connects about half of the top 500 machines, gets to the 80 to 98% is the top utilization number, which means that out of the theoretical 100% flops that you can get out of the machine that you build, you can actually use 90% and even more for the application, and only fraction of the compute power goes to the network. Comparing to Ethernet, where it is about 50% utilization, and newcomers GPU are not fully exploring the interconnect and capabilities, and it's also in some cases pretty low, and I'll talk about the optimizations for the GPU on the network in particular. Okay, so since about almost more than 2.5 years ago, we have introduced FDR, which is 56 gigabit per second InfiniBand network. And not only it gives obviously just raw bandwidth and latency better than 40 gig, here you can see actually the effect on the real applications. So the OpenFOAM Eclipse and LAMPS applications showing significant performance boost running on faster network, and not only just faster, but also it scales better as you add more processes and extend your cluster to larger amount of the nodes. So these network effects have not gone unattended by data center builders and the people that actually use the cluster to deliver the services. Microsoft Bing Maps, whoever uses it, and this is the very short list of companies that allow us to refer them as InfiniBand customers. They basically talk in public about at least part of the stuff, how they build their data centers. There's quite a few additional Web 2.0 and cloud companies that view IT as their competitive advantage, and they're much more secretive about how do they build the data centers. But PayPal, Microsoft, and there's other companies basically using InfiniBand. And interestingly enough, is that one company using InfiniBand cut down data recovery time from a week to 4 hours. So within half a day, you can get your database fully recovered in case of crash rather than a week, and it's obviously have a very significant impact on the business of this company. So the way we look at this is that actually the new trend of being able to deliver the services makes our world better. And there's a lot of analysis is done, and a lot of algorithms done in the healthcare. And it's interesting that there's a individual patterns RNA analysis takes 7 days. The goal was to cut it down only by 2 days. Using InfiniBand, you can actually get the RNA sequence data analysis within the 1 hour. So you can almost in real time analyze the RNA sequence and obviously draw the conclusions. So we can, using InfiniBand, we can find the pediatric cancer in this particular case much faster, and this can actually save human lives. So talking about a little bit on the past and the future, Mellanox powers half of the, or a little bit more than half of the petascale computers today across the globe. And the key thing is that it is pretty much standard off-the-shelf technology using the standard servers and uses standard InfiniBand interconnect. There is multiple entities are building very fast machines at very low cost. And the biggest machine in terms of the node count that was publicly announced is 20,000 node machine in NASA. So there is the flat layer 2 network that connects 20,000 endpoints running about 150,000 cores, CPU cores. And this actually in production in NASA for I think it's either 2 or 3 years now, running FDR and QDR InfiniBand, and there's multiple scientific and engineering projects running on this machine. Going from high-performance computing space to the cloud, today people use the cloud provider using the InfiniBand as their network for the cloud. Oracle, we work with Oracle since about 2002, 2003, since we have actually introduced our first InfiniBand solution. And all the Exalogic, Exadata, Exa everything in Oracle running InfiniBand inside with the bridging to Ethernet at high-performance bridging. Microsoft Azure running InfiniBand at about 90% efficiency of the cloud, and it is 2/3, so saving 1/3 of the application cost. ProfitBricks, AtlanticNet, and there's other cloud providers running InfiniBand as their network, and the reason they do it is they got much better ROI, return on investment, using InfiniBand from their infrastructure than using alternative interconnects like Ethernet. Actually, our first customer that we shipped our first InfiniBand device in 2001 was Network Appliance. They used InfiniBand as the backend cluster interconnect to connect their head nodes. And since then, we moving InfiniBand getting more and more adoption in the storage space. Right now, pretty much every storage vendor that building the storage servers are using InfiniBand as their cluster interconnect fabric. So you have client connectivity. Today, it's mostly Ethernet or fiber channel to the storage server, and this storage server is actually built as the cluster of processing nodes with the non-volatile storage behind it, be it flash or rotating disks, and all of them are using InfiniBand for faster access and lower cost and lower power. So, all the big and small storage vendors are using InfiniBand, and actually I think, at least in terms of amount of requests that we are getting to explore the technology, pretty much all the storage startups that are looking at new paradigm of using flash memory is using InfiniBand or looking at InfiniBand. So every 2.5 to 3 years, or 2.5 years, we managed to bump up the network speed by about factor of 2. We introduced 10 gigabit in 2002. About 2 years later, we introduced 20 gigabit and so on and so forth. We introduced 56 gigabit at middle of 2012, so a little bit more than a year and a half. So following this trend, you can basically draw your own conclusion, and we are going to have much higher network performance, 100 gigabit and above, on our roadmap. So the petascale is the FDR, and the exascale is going to be EDR and HDR machines, and we are working obviously with the people that are building these machines on the next wave of InfiniBand and Ethernet solutions, and I'll talk about Ethernet explicitly. So going to the higher speed, not saying that 56 gigabit on 4 lanes running is easy. It was really hard, but going even further, then it becomes even harder. So we are providing the end-to-end solution, including cables, since about 2005 or 2004, but we were not designing the cables. We are building the cables using commercially available components, and recently, so we were not owning the IP that is inside the cable. We were buying it and qualifying it. So recently, we bought 2 companies in the physical layer space in the silicon photonics. One is this company is Koturo, another one IPtronics. Koturo is a US company located near Los Angeles. IPtronics is a European company from Denmark. These two companies are working, have a silicon photonics solutions, and now we basically own all the IP from the very low level, from the cable, from the network all the way up to the application interfaces. So we can deliver the full solution, and we will design and qualify these 100 gigabit and beyond interconnects and links in the basically end to end. So the transceivers in the cables will be our design and our IP. I would like to talk about the recent Connect IB device, which is the first step to the exascale computing. And there are the challenges of scalability on the multiple fronts, and I'll talk about a couple of them. So it is the 7th generation of Mellanox interconnect adapter architectures. It is a dual-port FDR device, but it is capable of pretty much saturating both ports. So it can run 100 gigabit deliver and suck the 100 gigabit per second data rate from the server. And if you look at the IOPS, and actually this is what really gets to the performance, we can deliver, which actually measure it on the real system on the Sandy Bridge machines, 137 million messages per second. So if we talk about I/O operation, like storage access, that takes about three I/O operations, this device can deliver about 50 million I/O operations per second, which is about 2 orders of magnitude higher than any other network interface that is available today. And in addition to that, we have introduced the dynamically connected transport service, and I'll talk about this in a second. So in terms of just performance, we can saturate 2 ports of the FDR, so that's 100 gigabit per second single direction, or 200 gigabit per second bidirectional, and if it's about 2x higher than the most advanced ConnectX-3 FDR device that is available today, which can saturate only one FDR port. So, and this capabilities again, actually, it's showing just bandwidth and latency is great, but when you go to the real application, if this bandwidth and latency are not delivered efficiently enough to the application, it basically dwarfs and goes down somewhere, gets lost in the software stack and other inefficiencies. What you see here is that this is the actual applications running on the Connect IB and ConnectX-3, and what you see here is that Connect IB delivers better performance and it scales better, and the applications running on the Connect IB, they scale better when you add additional CPU power, which is number of nodes or number of processes. Okay, so one of the impediments of the scalability running InfiniBand is the memory footprint of the transport or the connection context. InfiniBand deploys a reliable connected model that was defined in the spec, and it takes some time to establish the connection. So it means that you need to connect all the processes up front, establish the connections to all the communicators up front, which means you need to allocate resources up front. And the amount of resources you need to allocate, if you're using the classic reliable connection model in InfiniBand that was defined in the first revision of the spec, basically you go through the roof of amount of memory you need, because every connection has its own context associated with this, so it takes memory, and this memory basically doing nothing, because you can build the cluster of 100,000 endpoints, but you never work or never communicate concurrently with 100,000 endpoints. and therefore the concurrency of communication is really a function of the CPU power and not function of the individual node and not function of the cluster size. So you established all these connections, you allocated resources, but in most cases you use a small fraction of this. So there was multiple attempts in the InfiniBand Trend Association and contextually Mellanox by mitigating this problem, introduced shared receive queue. This was in 2005, or XRC, Extended Reliable Connected Services, is 2008. So the idea behind these developments were to figure out how can we share resources across multiple processes, and this way reducing the number of resources you need. So it did the job. The scalability gets a little bit better, but still what was bothering us is that there is the amount of resources that an individual endpoint needs to have for communication is really a function of this individual endpoint compute power, or the concurrency it can actually deploy, and not the function of how many endpoints you can communicate with. Everybody can talk to everybody in the world, but we never talk to more than interactively, at least, to more than very small number of people. So in the Connect IB, we have introduced what we call dynamically connected transport service, and another way to look at it is on-demand connectivity. Okay, so if you can think about this is that there is the transport that delivers you all the reliable connected services like RDMA, atomics, and transport reliability, but it takes zero cost to establish the connection. So if I need to talk to some particular endpoint, the connection is established when it's needed, and when the messages exchange goes away, then the connection is steered down, and the resources are deallocated, can be used by another connectivity. So basically, you need to allocate as much resources as the endpoint can handle in terms of the concurrency it can handle. It has really nothing to do with the amount of endpoints it can communicate to. So it's as a result, in the Connect IB, the amount of memory that needs to be allocated to communicate is not a function of the size of the cluster, but it's pretty much the function of the concurrency that the individual endpoint can handle, which is in turn, the function of the CPU power. So we have this now balanced equation between the CPU power, the amount of memory that people build. It's also a function of the CPU power, and using this on the network doesn't mean that you need to allocate a memory according to the cluster size. In terms of latency, this is talking about cost of establishing the connection. What you see here is that latency, which includes the connection establishment, is about less than half of the Connect-X3 device. And obviously, when you go to the large messages, then connection established is even less significant. So it shows that this on-demand connectivity, it doesn't cost the performance. So it's the same latency as a reliable connected, but you don't need to allocate resources up front. Another impediment for scalability is some synchronization operations. And what happens is that when you need to synchronize the operations, then you can't really proceed further until all the nodes are synchronized. And if some endpoints had some disturbance like interrupts or some other jitters, then basically the slowest one dictates the system performance. OS jitter is, and people in the labs were actually changing the operating systems and the underlying infrastructure to reduce number of interrupts, which was the main source of the OS jitter. But building huge amount of memory, so page faults will not change, will not have a big impact on jitter. But basically, at the end of the day, it always exists. And if you do the barrier and collective operation on the same, on the same infrastructure, which means in the CPU running on, in the application running on top of operating system that runs on the CPU, you get this jitter, and the slowest one covers. So what we have done, we have implemented along with our friends in Oracle Oak Ridge National Lab. We have developed what we call Core Direct, which means you can actually offload the synchronization operation to the NIC. You program it up front, and therefore, if I'm running the CPU on the individual endpoint doesn't need to be a middleman and participate in the synchronization operation. Basically, synchronization operation is implemented in the network by the hardware that is designed in the network adapter, and it doesn't interfere with the processor. So here is the example of operations. It's the time goes from bottom up. So what you see here, there was some operation that ideally these operations were completed at the same time. Then the barrier takes effect. So now all this usually goes on the tree. Each one runs on the CPU and then notify to all the endpoints that synchronization is done, and they keep running. So in reality, what happens, each one of these endpoints got some other jitter, got some jitter, and as a result, this jitter is particularly bothering, because this guy is done. But the time he could take care about the message that was sent from the leaf of the tree, there was a jitter introduced that you have to wait, and therefore this jitter is actually a direct hit on the performance. What you see here is that these stars, it means that every NIC on the endpoint was pre-programmed to take care about the collective operation. So this guy can start off here, and despite of this jitter, it executes the collective operation and sends the result to the other endpoints. So you can actually see that jitter effect is taken care of, and overall system performance improves. This is another example. If you use synchronous versus asynchronous operation, when you want to even further overlap communication and synchronization, you can actually every time you get to the barrier, actually your NIC will do the job on its own, and you can go directly to the next iteration or next step of the process. So this is the example that actually using Core Direct, you can have much higher overlap between communication and computation than not using Core Direct, because basically you program this hardware in the network to do the synchronization, and the CPU is free to execute on the application. About 3 years ago, maybe 4 years ago, people started to use GPU as the floating point number cruncher. There's a huge amount of floating point units in the GPU, and people actually started to use it in the scientific calculations. The first GPUs that were used didn't have, didn't support double precision. It was really oriented to the graphics, but once people started to use the GPU in the scientific applications, now pretty much every GPU supports IEEE floating point standard. And but when you use the GPU, there is an intrinsic inefficiency when you cluster GPUs. The way GPU is designed is that it is DMA's data to memory and from memory, and then you cannot share the original design over here, if you want to send this data to the network, so the idea is that there is a multiple GPUs running on the different endpoints, and the data flows in between the compute engines. So in order to send the data that was calculated by one GPU to the next step on the other endpoint to be calculated by another GPU, what you need to do, you need to copy the data from the GPU to GPU buffer, then copy it from the GPU buffer to the network buffer, and then send it out. And on the receive side, it's basically you're doing the same copies but in different order. And this red one is the most painful one, because this is what CPU actually does on its own. This step is done by the GPU DMA. This step is done by the NIC DMA, but the red arrow is actually CPU moving byte from one memory location to other. So working with the GPU vendors, and by that time it was basically only NVIDIA. Now Intel also joins the pack. By changing the software model and mainly on the GPU, but also on the network driver, we allow to share the GPU and network buffers. So we got rid of the most painful part of this GPU to GPU communication. So GPU writes data to the memory, and the NIC can take the data from the memory directly and send it to the other side. It is really important that this side supports RDMA or as a target, because the data has to be placed in the right place. If it's just a simple interface, then you need always copy from the network buffer to the real destination buffer. This is the zero copy story on the network in general, and then GPU DMA can take it down. So this is the first step where we've implemented improved the most painful step in the GPU to GPU communication. But there is still some meat left, because GPU has a memory, and the data is moved from the GPU memory to the CPU memory, and then from the CPU memory to the host memory, and then from the host memory to the network, and the other side is the same. So there is an additional inefficient store and forward step, because ideally what you would want to do, you would take the data from the GPU and run it directly on the network. So this required some additional changes because both GPU and the NIC, they are designed to be DMA master and not DMA slave. The GPU vendors changed this or updated their design so GPU can be not only the GPU master but also GPU slave, and NIC can actually pull the data directly from the GPU memory and send it out and write it to the GPU memory directly on the other node. So DK Panda was here yesterday. These are our old friend from Ohio State University. He is the champion in the high performance computing in the academia. Basically, they're showing that there is a significant improvement both in latency and the bandwidth if use a GPU direct. But this is not the end of the. This is another example of not only the nuts and bolts and like people call hero number of the performance, showing the latency and bandwidth. This is also the execution of application. And you see that GPU Direct helps and improves the performance on the real application. Okay, so but that's not the story. Today, if you want to use GPU, you need to equip every server with the GPU hardware. And the usage of the GPU and the efficiency of using the GPU is not explored to the full extent. That you've seen actually on the top 500 list that the GPU-based servers efficiency is lower than others. And the reason is that you basically compute how much theoretical flops you can get, and there is a tremendous amount of flops you can get from the GPU, and then how much it's actually exposed in the application by running linpack in this case. So we have looked at this, and we thought that like people used to have disks local, and then now you have disks over the network. And the reason you can do it, and it actually efficiently, because the network access is negligible. Time of the network access, the bandwidth that you can get from the network, is sufficient to, so latency is negligible, and bandwidth is same as the disk bandwidth, so you can actually run the disk access over the network. That's not the case for the traditional networks. That's not the case for the high-performance I/O devices like GPU. GPU performance depends on the both latency and the bandwidth of the connectivity to the application memory, and therefore running GPU as the service or remote access to the GPU on traditional network is not something that can be perceived as attractive. With the FDR InfiniBand, both the latency and the bandwidth of accessing over the network becomes to be in the same ballpark of local access on the PCI Express. And what we have done with our friends from University of Spain is we have implemented GPU as a service, or basically tunneling the GPU commands, CUDA commands, over the network to the GPU, which is physically located on the different node than the client application processor. It's called DarCUDA, so you can imagine that like SCSI commands being tunneled through the network for block device over the network. Here we are tunneling GPU commands and data over the network to the GPU that is located on the other side of the network. So this was done through the InfiniBand FDR switches, and what you can see here, this is again the hero numbers of throughput in terms of megabyte per second. What you can get. Obviously, the Ethernet doesn't cut it. There is a lot of bandwidth that's not used on the network that you can use locally. And if you go to the InfiniBand, then with the FDR InfiniBand, you get very close to what you can actually, in terms of bandwidth, from versus what you can get when the local GPU access from the on the server itself. And this is another example for this from the raw numbers. This is to the application time for matrix products, multiplying 4,000 4K by 4K matrices. If you use it on the local GPU and on the remote GPU, the performance is very similar. If you run it over the traditional network, you're better off just use local CPU to compute it. So GPU over the network gives pretty much the same performance boost as the local GPU, but the advantage of having GPU over the network is now you can share this GPU hardware across multiple endpoints. So everyone that needs the GPU services can go to this GPU server and get his own GPU services. So once this technology will be deployed, I believe the GPU utilization numbers on the top 500 will go significantly up. So some other developments. Since 2007, we started the company, and our first multiple product generations were InfiniBand. And since 2007, we got to the Ethernet space with what we call that's just there's another example of the storage. The VDI is using RDMA. You can host 2x more VMs or 2.5x more VMs on the server, on the single server than otherwise. So you can have a much more efficient data center. This is sort of tight, connected to the Ethernet. We have introduced our first Ethernet device in 2007, and actually all our hardware can run either Ethernet or InfiniBand protocol. We call it VPI, Virtual Protocol Interconnect. And when we get to the enterprise data center and the storage, so people are not not everybody is willing to replace their Ethernet networks with InfiniBand, but having much more efficient interfaces for the application access to the network is attractive. So therefore, we can run InfiniBand stack or expose RDMA interfaces over either Ethernet or InfiniBand, and we can run obviously all the Ethernet protocols, and running iSCSI over RDMA significantly improves performance and both in latency and the bandwidth and the IOPS versus using it over Ethernet. So this is one example that you can actually run storage server and the compute server, and you can get from the virtual machine data rate close to the wire speed of the network. Our Ethernet developments are covering, again, we have end-to-end Ethernet solutions. I think we are the only company that can provide 40 gigabit Ethernet both on the endpoint NIC and the switch. On the Ethernet, however, there is the fairly significant amount of software and services that are exist in the network. And the way it's delivered today is the classic Ethernet companies like Cisco, Juniper, and the like. They provide vertical solution, and it resembles the early days of the computing, where you could got the box with the operating system and with the applications, and you can't really touch and do the mix and match on different components. So we have. We're now driving the initiative, it's called Open Ethernet, and actually we are not the only one. There's the whole industry momentum behind it. There are multiple companies that are delivering different components on the network stack on the switches, and the key is to put together the standard interfaces and the framework so you can mix and match different components and different services from different vendors. For example, if you like RSN Layer 2 stack and you want, Quagga or some other Layer 3 stack, today you can do it with the Open Ethernet. You can actually mix and match different components, and this is resembles of what is being done in the Linux and open source communities. So you can take the different models, the interfaces are well defined, and you can basically integrate the solution on your own and not necessarily taking it from the vendor. Actually, this is what Web 2.0 and cloud companies are doing. All of these companies from the both places are departing from buying expensive network equipment from classical network vendors like Cisco, and they're buying bare metal switches and bolt their software on top of it. So the key here is the framework and the interface, and that's what we are driving, and we actually submitted our APIs to the community already. So the Open Internet will enable to, like, in Linux there is a NetDev interface, and you can put any NIC underneath that, presuming that this NIC has the driver that exposes this interface, and you can run any network application on top of it. So the idea here is very similar. So we are standardizing the NetDev equivalent for the switches in the community, and on top of this interface, everybody can run its own software stack. So, going back, so far we have been able to introduce the network speed up every two and a half years, and we are fully poised to keep going. So we are going to introduce 100 gigabit EDR speed and further up, and I think exascale machine will need somewhere north of 400 gigabit per second networks, and we are in the development stages of delivering it on time. That's about it. Yeah.
Any questions for Mike? So which companies support Open Ethernet? Have you elaborated? And
Okay.
What's the relation with OpenFlow as well?
Okay, OpenFlow is the protocol or the way to communicate to the switches. And actually, it's very synergetic with Open Internet because you need to have an interface that is exposed by the switch, so OpenFlow controller can program the device. So, our marketing guys can elaborate about the list of the companies. They are aware much better than I do about this particular companies who is part of the Open Internet initiative. I can mention, Cumulus, for example. This is the classic Open Internet, or the spirit of Open Internet. PK8 is another one, and there is companies that are actually building their own equipment, which I mentioned, Web 2.0. These guys are fully behind this initiative. They just need the standard interface to get to the network, and all the rest they're doing on their own. Yeah.
So you said that when you use FBR, you get 96% CPU utilization. But comparatively, you're doing with 10 gig Ethernet. The 40 gig Ethernet, what's the utilization of CPUs?
Excuse me?
In one of your slides, you said with the InfiniBand FBR, you get 96% CPU utilization. On the same slide, you said with the Ethernet, you get like 50 to 80%. Is that at a 10 gig speed or at a 40 gig speed?
Well, the main thing about when we talk about Ethernet and InfiniBand in this context, it's not only just the link layer, okay, and the speed of the wire, but it also the traditional software stack that runs on top of Ethernet. So it includes, for example, TCP. Now we have, on different slides there's different Ethernet references. I think it's mostly 10 gig. There are some on the GPU Direct. There was 1 gig, but the issue with the CPU utilization on the 10 gig Ethernet is the transport stack. So if you go to the 40 gig, then the problem is getting even worse because it's pretty much per packet or per few packets the overhead, and when you have more packets per second, then CPU needs to work harder to process them.